My name is Luis Jofre. I'm a professor at the Technical University of Catalonia, UPC, in Barcelona. I'm going to talk about MIMO channel modeling. In certain cases, we are interested in optimizing the capacity of our communication system. In order to optimize the capacity of specifically a MIMO, multiple input, multiple output system, we know we have to optimize the antennas in themselves and the channel. So here we'll concentrate in characterizing the channel in between the transmitting and the receiving system, and to learn how to get independent and correlated radio channels that allow us to operate and produce an improvement into the capacity. In order to do that, we'll see two real examples. The first one taken at the Technical University of Sweden, KTH. Then the measurements were taken into the university indoor scenario, was the corridors of the department. So the measurements consisted on a frequency of 1.7 gigas, and they use for transmitting and for receiving antennas. The antennas were land over to a par, and the distance they covered when moving with the cart, you see, was in between 4 and 45 meters. So here you may see the system. You may see here 1 through 2, 3, 4 receiving antennas. They are land over to a par, and they kept walking through the corridor and measuring in a continuous way the received signals by the 4 receiving antennas that had produced at a certain transmitting location by the 4 two double polarized antennas. So here you may see the receiving card. They are calibrating and the transmitting card. And here you may see the corridor. So we plan to move with our receiving card through this corridor and measuring the received signal. So here you have a map of that. So we they were planning to move along a north hallway and a south hallway. We plan here just to show you this result was produced in the framework of a European joint research project some years ago. So we plan to move from the point number 4 to the point number 1 that's close to the transmitting. So the signals we'll get at the very beginning, they are much smaller than when the ones we get at the end when we are really close to the transmitter. So let's move and see. Look, wow, it seems a real mesh, but it's not such a thing. So in the horizontal axis, there is time, but we may put also distance. Is the time we move, then we may translate from time to distance. So that's the far away position. Then we were more far away from the transmitter, and at the end we were really close. And then we have in the 4 different colors, you may see in blue, green, red, and this kind of different blue, how there is a fading environment resulting of the combination of the different reflections on the walls, on the ground, on the roof, etc. And so you see different phenomena being combined, and then how they move, but there is a general component of increasing when we approach the transmitting position. So based on this, that's the matrix element measurements, the real ones. In fact, they are in amplitude and phase. Here we are just representing amplitude, but we have stock recorded in our memory also the phase ones. So we may extract the eigenvalues from that, and from that we may represent the capacity. There are two representations of the capacity. In fact, the blue is when we don't have channel statistical information, so we put the same power into the different channels. Or here we have in red when we have information of the channel, and you use that information in a proper way. We'll see in a moment what does it mean. That's the water filling method that we may see in a moment. So we see that when we use the knowledge of the channel, we improve a little bit the capacity. But here we may see the 1, 2, 3 eigenvalues of the channel. And then we see that there are two of them, the green one and the red one, that are a little bit stronger than the other ones. In fact, we may see that our channel, even when we have 4 transmitting and 4 receiving antennas, the real independent channels that is possible to get from this particular scenario is not 4, but just 2 main single values. So when we calculate the capacity that we get for those eigenvalues, again we get in blue and red the capacity, that's the average capacity of our system. So what we learn here is that at the end, the number of independent radio channels we have in a system depends on the number of elements and depends on the characteristic of our channel. For this particular case, you may see that's a long corridor. At the end, the signals are strongly correlated, so we are able to extract 2 independent radio channels, but no more than that. That's the first example. Let's take a look to a second example. That corresponds to an underground metro tunnel of communication system in Barcelona. The system is planned to get unmanned trains. So because the trains are unmanned, we have to be sure that the communication systems is alive all the time. So we need a lot of robustness. And then we studied let's say, the behavior of the channel. So again, we use 4 antennas through 2 meters apart, 2 meters above ground, located into the tunnel. Here you may see a real picture, and here the map. That's the upper and lower tunnels for the 2 sense to direction of circulation of the trains. So let's see what happens, how many radio links, how many independent channels we are able to get from those systems operating this time 900 megahertz. So when we do, and here on your let's say left hand, you may see that's the real field strength representation as a function of the distance from 0 to 300 meters. We were interested into getting a coverage distance of at least 250 meters. So this line represents 250 meters. So that's the signal we get produced by each of the transmitting antenna. When the transmitting antenna is antenna number 1, that's the signature, that's the field distribution into the tunnel. That's the field distribution for the antenna number 2, for the antenna number 3, and for the antenna number 4. Because those were simulated results, you may see that the antenna number 1 and the antenna number 4 produce the same, and identically antenna number 2 and antenna number 3. So we calculate from a numerical point of view the eigenvalues, and then remember that in the ideal case, the eigenvalues couldn't be 1, 1, 1, 1. That would be the ideal case for equally weighted independent channels, but what we get is the first two ones, 2.4, 1.4 eigenvalues are strong enough, but the next ones, 0.13 and 0.05, are really low. So again, what we see is that our channel has just two real independent radio channels to be used as a MIMO. And then here on your right, you may see the capacity that you get for each one of those eigenvalues. And the values are 2.8 bits per second per hertz, 2.2 that are quite good, and then 0.4 and 0.2. So, and here you may see what are those eigenvalues. You see that that's the eigenvector corresponding to the first eigenvalue. So you see that's kind of a horizontally constant field, and this is kind of odd mode, positive and negative. And the other ones you may see how at 250 meters from the transmission set, from the transmitter antennas, they are almost zero. So in fact, you have again two realistic radio links, even though you use for transmitting and for receiving antenna. At the end, you'll be able just to take advantage of just two eigenvalues and then two eigenvectors, so two radio links. Thank you for your attention.